All right, we're back. Hello, everyone. So now we are talking about common distributions. So we're moving past the simple examples that we had so far. We're moving to like more complex examples. Now we're basically combining what we just did with the probabilities and the random variables and combining that with a bit of combinatorics. Yeah, so that's the idea. So we are gonna talk about 5 to 7 distributions here. This lecture we're gonna make a start with binomial Poisson distribution. They're discrete distributions, and that also makes them a little bit more easy to understand and a bit more intuitive. And next time we're gonna go to hypergeometric. You probably haven't heard of that one yet. The normal distribution, like the whole world uses the normal distribution for lots of things, so that's going to be our main focus next time. And we're going to talk about Weibull next time. That's an important one for quality management. And yeah, we're also going to brush on chi-square, student t, like other distributions. So next time the more continuous ones, this time binomial Poisson. Right, let's dive right in. Binomial distribution. It all stems from a coin toss. In a time when it was developed, Bernoulli kind of developed this further, and he assumed something that kind of resembles a coin. So your omega, your sample space, only consists of A and not A. So there are only two outcomes, just like a coin, heads or tails. So could be the simple analogy. Yeah, and we do that repeatedly, multiple coin tosses, and they're all obviously independent of each other. Let's for a start say we've got a fair coin. Yeah, and what are the chances of getting 3 heads? Well, every time same chance. Every time we've got the chance of 1/2 times 1/2 times 1/2 is 1/8. That's our chance with a fair coin. Okay, so what changes if it's not a fair coin, or if we just want to introduce the probabilities P and Q. So P is the probability for heads, and Q is the probability for tails, which is 1 minus P. Then we can just write the whole thing. Probability for 3 heads is P to the 3, P cubed. Right, still nothing's really changed. So what about a different event? What about 2 heads and 1 tails? And that seems a bit easier because there are multiple options. With 3 heads, it always has to be definitely a head each toss. But with like 2 heads, 1 tails, the tails could be the third toss, or it could be in the second toss, or in the first one. So we've got like kind of 3 scenarios that all lead to the same result. Still, every time we multiply the possibilities, so 2 times heads and 1 times tails, but we've got 1, 2, 3 possibilities to achieve that, and this 3 here, that's this 3 here at the beginning. Okay, how do we know it's 3? Well, here it's easy, but from last time we know we can express this number in general as like 3 choose 1. Yeah, so the permutations without repeating. Okay, cool. So we get this formula, and now all we do, we generalize this. Now here we've been tossing 3 times. Yeah, now we generalize that, and there is the binomial distribution. That's really all there is to it. So if we say x is a random variable that's distributed binomially, yeah, this here means this kind of little symbol. It means distributed as binomial. And now the chance of k successes, and successes are the heads, yeah, or what we called A, outcome A, that has the probability P. If we try n times, that is just an analogy to earlier, yeah, n choose k. Yeah, those are the number of scenarios that lead to the same result, and then successes to the power of k times the not successes times the tails to the power of n minus k. That's the whole formula, and that gives us the probability of k successes, and this is called the binomial distribution. So this here obviously is the probability mass function, probability mass function or mass distribution. Yeah, FB, and it has 3 parameters. It has the number of successes, the number of trials total, and the probability. And yeah, different literatures and computer programs use like slightly different order of these 3 parameters, so watch out. What does it look like? Binomial distribution, it looks like that, like a little pyramid, obviously with 50% heads and tails. 5 successes, 5 heads is the most likely one, yeah, which kind of agrees with what we would expect. Expectation value would be 5, 10 tosses with 50%, and yeah, and then everything else becomes quite unlikely. So only 1% that we only get 1 tails, and very, very unlikely we don't get any tails. Okay, what's the CDF like? Obviously it's a valid CDF. It starts at 0, goes up to 1, and is monotonically increasing. The CDFs, to be honest, they're kind of mathematically the most powerful bit. Yeah, we're going to calculate a lot with them, but visually there's not much in the CDFs. You will see like all the distributions all look same. Kind of the key is in like some little detail of how this curve comes up. You won't really see it with the bare eye. So we normally look at the PDFs or PMDs to kind of get a bit of a visual sense of the distribution, but the CDFs that look pretty boring. Good. Now we can do one thing. We can just like tweak a little bit. Let's just keep the number n constant for the time being, but change the probability. So with 40%, now suddenly 4 is the highest likelihood outcome, obviously, and my distribution kind of starts to shift. That also makes it a bit asymmetric, but it's still hard to see. Let's carry on. Let's go down to 0.3, 0.2, and you can see 2 is the most likely, as we expect. But now we see this asymmetry. So it's, yeah, from 3, if you think that's the center, it only goes down to 0.27, but it goes down to 0.2 to larger numbers. So now we find like a large asymmetry, like kind of you get this long distribution to the right and this fairly short one, obviously, because we're limited by 0 to the left, and that carries on if we decrease it even further. So this is what binomial looks like. Let's see what we can do with that. So I have to explain this a little bit. Well, the question is, what is the probability of getting 5 heads in 8 coin tosses, where heads has this 75% chance? Now, you at home, you can pause the video and calculate that with Excel or MATLAB or whatever program you want to use. That's absolutely perfectly fine. Like in a normal lecture and also in the exam, obviously we won't have computers available. So what we do, we work with tables. So I just quickly want to explain what this table does. It basically gives you the probabilities by, you first look up P, and you can choose between 0.1 up to 0.9 in little steps. There are also more detailed tables, but we don't need it more detailed at the moment. And yeah, so we look up this one here, and then here on the right, obviously I've given you the one that has n equals 8, because we've got 8 coin tosses, and this here is x. X means the number of heads. Okay, so now you should have a rough idea how to use this table. So have a go. Yes, perfect. Obviously it's 0.208, the probability. How do we find it? Well, easy. 0.75 is the probability. We find it here. And we've got the 5 heads. 5 heads here. So we follow that line over here. And that one down. So our answer is exactly there. N equals 8 was kind of a given in this table. Yeah, and if you're using any other program, you will have gotten like the same result, more or less. Right, let's try another one. What is the probability of getting 3 even numbers when rolling a fair die 8 times? Okay, so now we have to do a bit of translation to adapt it to this Bernoulli trial, because a die has more outcomes, but we're kind of flattening them. We're just interested in even or odd. Have a go. Perfect. So the probability of an even number is 50%. Yeah, 3 out of the 6 numbers are even, 2, 4, 6. And then we just do the same thing. So P 50%. We go down this aisle, and we want 3 even numbers. So x equals to 3. Cross over, and here's our answer. Yeah. So as a distribution, is like the Bernoulli distribution, k or x equals 3, n equals 8, probability 1/2. Perfect. One more. What is the probability of getting at least 6 heads in a coin toss? Interesting. So at least 6, that means it could be 6, it could be 7, or it could be 8. Yeah, because we're doing 8 maximum. So how do I calculate this? Basically I can just add the probabilities. Yeah, for 6 6, 7, and 8, each time with the right parameters. I can find them down here, so we're at probability 0.6, so we're adding these three numbers, yeah, and that's the result here. What we could also do, at least on a computer program, is we say, okay, I don't have the cumulative probability up to 8, but I have the cumulative probability down to 0. So I know that the probability of like 6 up to 8 is 1 minus the probability of 5 down to 0. So I can express it in this way here, 1 minus, and this is the cumulative, this is the CDF. And that should give the same result if you're in Excel or any other program. Good. Let's have a quick look, a bit more detail about the binomial distribution. So interesting about it is it approximates the normal distribution. So if we go to large n's, you would see, and maybe the shape was already a little bit familiar, it kind of converges towards this like Gaussian bell shape. It is hard to calculate for large numbers because there are factorials in the binomial coefficient. There's like n choose k. That's why we will use normal distribution fairly soon if the number n goes large. It makes it a lot easier. And there's also like a multinomial extension if you ever need that, basically multi-dimensional analogy. Okay, expectation value is n times p. Yeah, as we've seen, so probability 40%, 10 tosses means expectation value is 4. Yeah, not really surprising. The variance, don't want to show you the proof, but it's a nice simple formula, n times p times q. Alright, let's just try it out. What is expectation value and variance from 4 coin tosses with this probability? That was easy. Yeah, n times p is 4 times 0.3, so expectation value is 1.2, and variance you just multiply it with 0.7 and you get this. So really easy to calculate. Could we back this up? We could try it, or you can try it at home if you like, to calculate expectation value, and maybe if you're keen, the variance as well, just from like first principle formula, using those numbers in the table. They're basically the probabilities of our AJs, and it should come up as well. So for the expectation value, I've kind of shown it to you down here. Here, these are my these are the AJs, 1, 2, 3, 4. And where's the probability? 0.3 is the probability. Okay, so I'm adding these numbers here. We don't need the top one because it's 0 times 0.24. And the result is the same. So brilliant. Yeah, it works. In general, you can use the binomial distribution on MATLAB. Bino PDF gives you the probability mass function, and Bino CDF the probability distribution, and MN PDF is multinomial if you're interested. Excel kind of has binom.dist as well. Good. That's all we need to know for binomial. Coming up in the next video, the Poisson.